Webb just revealed something massive. A Nobel Prize winner is now warning that the James Webb Space Telescope is showing us a universe dramatically different from what we expected. Forget everything you think you know about the early cosmos. The data reveals structures that shouldn't exist, galaxies too mature, too early. It challenges the very foundation of our cosmological models. Are we on the verge of rewriting the textbooks? The evidence shows a universe far stranger and far more complex than anyone dared imagine. The implications extend to our understanding of dark matter, dark energy, and the fate of the universe itself. 600 galaxies, all breaking the rules. That's not hyperbole. That's the stark reality revealed by the James Webb Space Telescope. These aren't just any galaxies, they're early galaxies dating back to within the first billion years after the Big Bang. And they're far too massive, far too bright, and far too evolved for what our current cosmological models predict. Consider the timeline. Our understanding of galaxy formation hinges on the gradual accumulation of matter. Small clumps merge to form larger structures, eventually evolving into the spiral and elliptical galaxies we see today. This process, driven by gravity and influenced by dark matter, takes time, billions of years. Yet Webb is showing us fully formed behemoth galaxies existing when the universe was still in its infancy. It's like finding fully grown oak trees sprouting from the ground mere weeks after the first acorn was planted. It defies logic. It challenges the very foundation of our understanding of how galaxies assemble. These early galaxies possess stellar populations that are surprisingly mature. They harbor elements heavier than hydrogen and helium, elements that should only be forged in the hearts of massive stars and dispersed through supernova explosions. For these elements to exist in such abundance in the early universe suggests that star formation occurred at an incredibly rapid pace, far exceeding the rates predicted by our simulations. The sheer size of these galaxies is equally perplexing. Some are comparable in mass to the Milky Way, our own galaxy, which has had billions of years to grow. Finding galaxies of this size so early in the universe suggests that the conditions for galaxy formation were far more efficient, or that our understanding of the initial conditions of the universe is incomplete. One of the most significant challenges posed by these observations is the implication for dark matter halos. Dark matter, an invisible substance that makes up about 85% of the matter in the universe, is thought to play a crucial role in galaxy formation. According to our models, galaxies form within vast halos of dark matter, whose gravity pulls in gas and other matter. However, for galaxies to grow as large as those observed by Webb in such a short period, they would require dark matter halos that are far more massive than our current models allow. This discrepancy raises questions about the nature of dark matter itself and whether our understanding of its distribution in the early universe is accurate. It's not just the size and maturity of these galaxies that are causing headaches for cosmologists. It's also their abundance. Webb is finding far more of these early, massive galaxies than expected. This overabundance suggests that our models are missing a key ingredient, or that there is something fundamentally wrong with our understanding of the physics that governs galaxy formation. The data reveals a universe that is far more efficient at forming galaxies than we previously thought. It suggests that the early universe was a much more active and dynamic place, with star formation rates and galaxy mergers occurring at a frenetic pace. These observations have profound implications for our understanding of the cosmic timeline. They force us to reconsider the sequence of events that led to the formation of the galaxies we see today. They challenge the notion that galaxy formation is a slow and gradual process, suggesting that it can occur much more rapidly under certain conditions. And what are those conditions? That's the million-dollar question. Are we missing a key physical process that accelerates galaxy formation? Is our understanding of dark matter incomplete? Are there other factors at play that we haven't even considered? One possibility is that our understanding of the initial conditions of the universe is flawed. Perhaps the early universe was not as homogeneous as we thought, with certain regions being denser and more conducive to galaxy formation. These overdense regions could have acted as seeds, allowing galaxies to grow more rapidly than in other areas. Another possibility is that our understanding of feedback processes is incomplete. Feedback refers to the effects that star formation and supermassive black holes have on their surrounding environment. These processes can either suppress or enhance galaxy formation, depending on their strength and duration. If feedback processes were weaker in the early universe than we currently believe, it could have allowed galaxies to grow more rapidly. Alternatively, if there were other feedback mechanisms at play that we haven't yet identified, they could also have contributed to the accelerated formation of these early galaxies. The implications extend far beyond the realm of galaxy formation. If our understanding of the early universe is fundamentally flawed, it could have ripple effects throughout cosmology, affecting our understanding of dark energy, the expansion rate of the universe, and even the ultimate fate of the cosmos. Consider this. If the early universe was more dynamic and chaotic than we thought, it could affect our measurements of the Hubble constant, which is a measure of the expansion rate of the universe. There's already a tension between different measurements of the Hubble constant, and these new observations could exacerbate that tension. The analysis continued. Scientists are now scrambling to refine their models and simulations to account for these unexpected observations. They're exploring new physics, re-evaluating existing theories, and searching for clues that can help them unravel the mystery of these early, massive galaxies. This isn't just a minor tweak to our existing models. This is a fundamental challenge to our understanding of the universe. It's a call to arms for cosmologists, astrophysicists, and particle physicists to work together to solve one of the biggest puzzles in modern science. And while the challenges are immense, so too are the opportunities. By confronting these discrepancies and pushing the boundaries of our knowledge, we can gain a deeper understanding of the universe and our place within it. Meanwhile, every new image from the James Webb Space Telescope brings more surprises, more questions, and more challenges. The universe, it seems, is far more complex and mysterious than we ever imagined. This means that the standard lambda CDM model is now facing new challenges. While it's been the prevailing model for decades, explaining a wide range of cosmological observations, the Webb data suggests it may need significant revisions or even a complete overhaul. The lambda CDM model relies on the existence of cold, dark matter, CDM, and a cosmological constant, lambda, to explain the accelerating expansion of the universe. However, the overabundance of massive galaxies in the early universe could indicate that dark matter is not as cold as previously thought, or that there are other factors at play that are not accounted for in the model. Ever wonder why the math doesn't add up? Because when it comes to the early universe and galaxy formation, the numbers are looking increasingly off. Specifically, there's something called the stellar mass anomaly that's got astrophysicists scratching their heads. Essentially, it boils down to this. The James Webb Space Telescope is finding galaxies in the early universe. We're talking within the first billion years after the Big Bang that are far more massive than our current models predict they should be. We're not talking about slightly bigger. We're talking about galaxies that are packing 10 times, 100 times, even 1,000 times more stars than they should, given the age of the universe at that point. That's not a small discrepancy. Think about it like this. Imagine you're baking a cake and the recipe says it should take 30 minutes in the oven. But when you pull it out after only 10 minutes, it's already fully baked and 3 times the size it's supposed to be. You'd probably double-check the recipe, your oven, and maybe even question the very nature of baking itself. That's kind of where we are with these early galaxies. Our understanding of how galaxies form relies on a few key principles. We believe that galaxies grow gradually through the accretion of smaller clumps of matter, merging with other galaxies, and the steady formation of stars within their gravitational pull. This process takes time, a lot of time. The early universe, however, was a cosmic infant, still in its very early stages of development. There simply shouldn't have been enough time for these behemoth galaxies to have assembled themselves. So, what could explain this anomaly? There are a few leading hypotheses, each with its own set of implications. One possibility is that our understanding of star formation in the early universe is incomplete. Perhaps stars formed much more rapidly and efficiently than we currently believe. This could be due to differences in the composition of the gas clouds from which stars are born, or perhaps the presence of exotic particles that catalyze star formation in some way. If stars formed faster, galaxies could have reached their observed masses more quickly. Another hypothesis revolves around the nature of dark matter. As previously mentioned, the lambda CDM model assumes that dark matter is cold, meaning that its particles move relatively slowly. This allows dark matter to clump together more easily, forming the gravitational scaffolding upon which galaxies are built. However, if dark matter were warmer, meaning its particles move faster, it would be more difficult for it to clump together, potentially suppressing the formation of small galaxies and favoring the formation of larger ones. A third possibility is that our measurements of the distances to these early galaxies are off. Distance is crucial for determining a galaxy's luminosity and, consequently, its mass. If these galaxies are actually closer than we think, their intrinsic luminosity and mass would be lower, potentially resolving the anomaly. However, independent distance measurements based on different methods have generally confirmed the original estimates, making this explanation less likely. And then there's the really unsettling option. What if our entire understanding of gravity is wrong? We base our models on Einstein's theory of general relativity, which has been incredibly successful in explaining a wide range of phenomena. But what if general relativity breaks down at the extreme conditions that prevailed in the early universe? This would require a major paradigm shift in our understanding of physics, but it's not entirely out of the question. These are massive question marks hovering over everything. Here's what's wild. Some researchers are even suggesting that the very nature of dark matter itself might be different than what we currently think. Instead of being made up of weakly interacting massive particles, WIMPs, which are the leading candidate for dark matter, it could be made up of axions, sterile neutrinos, or even primordial black holes. Each of these alternatives would have different implications for galaxy formation. Further examination revealed that some of these early galaxies are not only massive but also incredibly compact, with their stars packed much more densely than in typical galaxies. This raises even more questions about how they could have formed so quickly and efficiently. It's like trying to cram the population of a major city into a tiny village. It just doesn't seem physically possible. The implications extend beyond just the formation of galaxies. If our understanding of galaxy formation is flawed, it could also affect our understanding of the evolution of the universe as a whole. Galaxies play a crucial role in shaping the intergalactic medium, enriching it with heavy elements produced in stars. If galaxies formed differently in the early universe, it could have altered the chemical composition of the intergalactic medium, which in turn could have affected the formation of subsequent generations of stars and galaxies. Scientists discovered that the James Webb Space Telescope is pushing us to reconsider fundamental aspects of the lambda CDM model. And it's not just one thing, it's a confluence of factors that are creating this crisis. The stellar mass anomaly is just one piece of the puzzle, but it's a particularly glaring one. It highlights the fact that our current models are simply not up to the task of explaining the universe we're seeing through the eyes of Webb. This kept me up last night. I couldn't shake the feeling that something fundamental about our understanding of the universe might be off. We've always thought of dark matter as this scaffolding, this invisible framework upon which galaxies form. It's the silent partner in cosmic evolution, pulling things together through gravity. But what if its role isn't quite what we envisioned? What if it's more nuanced, more complex, even different? The lambda CDM model, our current best guess at how the universe works, predicts a certain distribution of dark matter in galaxies. Specifically, it anticipates a dense concentration of dark matter at the center of galaxies, a sort of gravitational anchor that helps to hold everything together. This concentration is known as a cusp. However, some observations, particularly those made on dwarf galaxies, smaller, fainter galaxies that often orbit larger ones, have suggested that the dark matter distribution isn't quite so cuspy. Instead of a dense concentration at the center, these galaxies seem to have a core, a region of relatively constant dark matter density. This discrepancy is known as the core cusp problem. Now, the James Webb Space Telescope is throwing a wrench into the works. Its unprecedented ability to observe the earliest galaxies is providing us with a new perspective on galaxy formation, and the data is perplexing. These early galaxies, which formed within the first few billion years after the Big Bang, are far more massive and mature than our models predict. This suggests that galaxy formation was far more efficient in the early universe than we previously thought. So, where does dark matter fit into all of this? Well, if galaxies formed more quickly and efficiently, it might imply that dark matter played a different role than we currently believe. Perhaps it wasn't just a passive scaffolding, but an active participant in the formation process. Maybe it interacted with normal matter in ways we don't yet understand, accelerating the collapse of gas and dust into stars. Consider the possibility that dark matter self-interacts. In other words, the particles that make up dark matter can collide and scatter off each other. This self-interaction could potentially flatten out the central cusp of dark matter halos, creating the core that we see in dwarf galaxies. Some theorists propose that these interactions could transfer energy from the dense, central regions of dark matter halos to the outer regions, effectively smoothing out the distribution. This has huge implications. Furthermore, if dark matter interacts with normal matter through some unknown force, it could also affect the formation of galaxies. For example, if dark matter particles can scatter off of normal matter particles, it could slow down the collapse of gas and dust in the early universe. This might seem counterintuitive, but it could actually lead to the formation of more massive galaxies. By slowing down the collapse, dark matter could allow more gas and dust to accumulate before stars begin to form. This larger reservoir of material could then lead to the formation of a more massive galaxy. The other alternative is that dark matter is doing something completely different, something we aren't even considering. And then there's the possibility that our understanding of gravity itself is incomplete. General relativity, Einstein's theory of gravity, has been incredibly successful in explaining the behavior of the universe on large scales. However, it might not be the whole story. Some physicists have proposed modified theories of gravity which suggest that gravity behaves differently on galactic scales than on smaller scales. These theories could potentially explain the observed distribution of dark matter in galaxies without invoking dark matter at all. One of the most well-known modified theories of gravity is modified Newtonian dynamics, ARMOND. ARMOND proposes that at very low accelerations, such as those experienced by stars in the outer regions of galaxies, gravity deviates from Newton's law. This deviation could explain the flat rotation curves of galaxies, which are one of the main pieces of evidence for dark matter. However, MOND has its own problems, and it doesn't explain all of the observations that support the existence of dark matter. It's a complex web of possibilities, each with its own set of challenges and implications. The James Webb Space Telescope is providing us with the data we need to start untangling this web, but it's also revealing just how much we don't know. We're peering into the early universe with unprecedented clarity, and what we're seeing is both exhilarating and humbling. Measurements showed that the very early galaxies are far more massive than lambda CDM allows. The idea that dark matter might not be what we think it is, that it might play a more active or nuanced role in galaxy formation, is not new. But the observations from the James Webb Space Telescope are lending new weight to this idea. They're forcing us to reconsider our assumptions about the nature of dark matter and its role in the universe. Here's what's wild. If dark matter does self-interact or interact with normal matter, it could have profound implications for our understanding of particle physics. It could open up new avenues of research and lead to the discovery of new particles and forces. It could also help us to solve some of the other mysteries of the universe, such as the nature of dark energy. The implications extend beyond just the realm of astrophysics and cosmology. Understanding the true nature of dark matter could also have practical applications. For example, if we could learn how to manipulate dark matter, we might be able to use it to create new technologies such as advanced propulsion systems or new forms of energy. This means the universe is far more interconnected than we previously imagined. The analysis continued. The data started to pile up. There was a clear and present signal. This is a call to arms for scientists around the world. We need to develop new models, new simulations, and new experiments to test our understanding of dark matter and galaxy formation. We need to be open to new ideas and willing to challenge our assumptions. The James Webb Space Telescope has opened up a new window on the universe, and it's up to us to explore it. And then the theorists got involved. Further examination revealed something even more peculiar. December the 12th, 2022. A small group of astrophysicists huddled around a monitor at the Max Planck Institute. The latest simulations were running, attempting to reconcile the JWST observations of early galaxies with the lambda CDM model. The mood was tense. Hopes were high, but skepticism lingered. Days turned into weeks, and the simulations kept failing. Not just failing in minor ways, but failing spectacularly. The simulations simply couldn't produce galaxies as massive and as well-formed as the James Webb Space Telescope was seeing, and seeing them so early in the universe's history. It was as if the universe had completely ignored the script that scientists had written for it. Galaxies were appearing far too quickly, far too massive, and with far too many mature stars. They shouldn't even exist, according to our best understanding. The problem wasn't just with one or two galaxies, it was a systemic issue appearing across a wide range of observations. The early universe, as revealed by the James Webb Space Telescope, was fundamentally different from what our simulations predicted. Now, simulations in astrophysics are incredibly complex beasts. They involve modeling the interactions of billions of particles, accounting for gravity, gas dynamics, radiation, and a whole host of other physical processes. They're like incredibly intricate virtual universes built to test our theories and predictions. When simulations fail, it means there's something fundamentally wrong with our understanding of the underlying physics. In this case, the failure pointed to a crisis in our understanding of galaxy formation and the role of dark matter. Consider the implications. If the simulations can't reproduce the observed universe, then our entire theoretical framework is called into question. It's like trying to build a house with faulty blueprints. No matter how hard you try, the house will never stand up straight. And the scientists involved knew it. The lambda CDM model, while successful in many respects, relies on certain assumptions about the nature of dark matter and its interactions with normal matter. These assumptions are baked into the simulations, and if they're wrong, the simulations will inevitably fail. The question then becomes, what are we missing? What crucial ingredient is absent from our models? What fundamental misunderstanding is preventing us from accurately simulating the universe? Some scientists began to explore alternative models of dark matter. Perhaps dark matter isn't as cold or inert as we thought. Perhaps it interacts with itself or with normal matter in ways that we don't yet understand. Other scientists started questioning the initial conditions of the universe. Maybe the early universe was more inhomogeneous than we previously assumed, with regions of higher density that could have seeded the rapid formation of galaxies. Still, others began to explore modifications to the laws of gravity. Perhaps general relativity, Einstein's theory of gravity, needs to be modified at very large scales to account for the observed behavior of galaxies and the expansion of the universe. The mood at conferences shifted. There was a palpable sense of excitement and uncertainty. The James Webb Space Telescope had thrown a wrench into the works, forcing scientists to rethink some of their most cherished assumptions. It's important to understand that this kind of crisis is not necessarily a bad thing. In fact, it can be a catalyst for progress. When faced with a major discrepancy between theory and observation, scientists are forced to be more creative, more innovative, and more open to new ideas. It's during these times of crisis that some of the greatest breakthroughs in science occur. The analysis continued, but the pressure was mounting. The sheer volume of data coming from the James Webb Space Telescope was overwhelming, and scientists were struggling to keep up. New papers were being published at a dizzying rate each, presenting new observations and new interpretations. The problem wasn't a lack of data, it was a lack of understanding. Scientists were drowning in information, but they couldn't make sense of it all. They needed a new framework, a new paradigm to explain the strange and unexpected universe that the James Webb Space Telescope was revealing. And then a new paper emerged from a team at Cambridge. It proposed a radical new idea, that the early universe was dominated by something called fuzzy dark matter. Fuzzy dark matter, unlike traditional cold dark matter, is made up of extremely light particles that behave like waves rather than particles. These waves can spread out and interfere with each other, creating a smoother distribution of dark matter that could potentially explain the rapid formation of galaxies in the early universe. The Cambridge paper generated a lot of buzz. It was a bold and unconventional idea, but it seemed to offer a possible solution to the crisis created by the James Webb Space Telescope. But the fuzzy dark matter hypothesis wasn't without its challenges. It required a very specific type of dark matter particle, one that hadn't yet been detected, and it had to be carefully tuned to match the observations. Still, it represented a significant step forward. It showed that scientists were willing to think outside the box and explore new ideas in order to reconcile theory with observation. Scientists discovered that even the distribution of dark matter within these early galaxies was perplexing. Simulations predicted a smooth, centrally concentrated distribution, but the James Webb Space Telescope observations suggested a more clumpy, less concentrated distribution. This discrepancy further challenged the standard model of dark matter and galaxy formation. The implications of these simulation failures are profound. It suggests that our current understanding of the universe is incomplete and that we need to develop new theories and models to explain the observations from the James Webb Space Telescope. It's a humbling reminder of how much we still don't know about the cosmos, and a testament to the power of scientific inquiry to challenge our assumptions and push the boundaries of knowledge. The universe, it seemed, was even stranger than we had imagined. It was a different universe indeed, one that demanded a new way of thinking. And the theorists? They were just getting started. We thought redshift was a reliable indicator of distance. But what if it isn't? Redshift, for those who aren't deeply immersed in cosmology, is the stretching of light waves as they travel across the expanding universe. Think of it like the Doppler effect, but for light instead of sound. The farther away a galaxy is, the more its light is stretched, and the redder it appears to us. This has been a cornerstone of our understanding of the universe's scale and age. The James Webb Space Telescope, however, is throwing a wrench into this neat and tidy picture. It's finding galaxies at redshifts that, according to our current models, should be impossibly far away and impossibly bright. Galaxies that should have taken billions of years to form appear to have popped into existence in a cosmic blink of an eye. So, what's going on? Is our understanding of redshift flawed? One possibility is that there are other factors besides the expansion of the universe that can cause redshift, factors we aren't fully accounting for. Perhaps the light from these early galaxies is interacting with something along its journey to us, something that's stretching the light waves and mimicking the effect of distance. Consider, for example, intergalactic dust. While space may seem empty, it's actually filled with a sparse but pervasive amount of dust and gas. If this dust is somehow different in the early universe than it is today, it could be affecting the light from distant galaxies in ways we don't yet understand. It could scatter certain wavelengths of light, making the galaxies appear redder and thus artificially inflating their redshift. Another more radical possibility is that the fundamental constants of nature aren't as constant as we think they are. The speed of light, for example, is a cornerstone of physics. But what if the speed of light was slightly different in the early universe? This could affect the way light propagates through space and alter the redshift of distant galaxies. It's a controversial idea, to be sure, but it's one that some physicists are actively exploring. João Magejo, a professor of theoretical physics at Imperial College London, has long championed the idea of a varying speed of light. He argues that it could solve several cosmological problems, including the horizon problem, which asks why the universe is so uniform in temperature, even though different regions should never have been in causal contact. Magejo's ideas have often been met with skepticism, but the James Webb Space Telescope observations are giving them a new level of credibility. If the telescope is indeed seeing galaxies that are too bright and too massive at high redshifts, then perhaps it's time to seriously reconsider our assumptions about the constancy of the laws of physics. Of course, it's also possible that there's a more mundane explanation for the James Webb Space Telescope observations. Perhaps we're simply misinterpreting the data. Perhaps the galaxies aren't as far away as we think they are, or perhaps they're not as bright. It could be that our calibration of the telescope is slightly off, or that there are subtle biases in our data analysis that we haven't yet accounted for. Astronomers are meticulously checking and rechecking the data, looking for any possible sources of error. They're comparing the James Webb Space Telescope observations with those from other telescopes, such as the Hubble Space Telescope and ground-based observatories. They're also developing new techniques for analyzing the data in order to extract the most accurate information possible. The bottom line is that we don't yet know for sure what's causing the discrepancies between the James Webb Space Telescope observations and our current models of the universe. But one thing is clear: something is amiss. Our understanding of redshift may be incomplete, and we may need to revise our understanding of the universe's expansion, the properties of intergalactic dust, or even the fundamental constants of nature. This isn't necessarily a bad thing. In fact, it's precisely these kinds of discrepancies that drive scientific progress. It's when our observations clash with our theories that we're forced to rethink our assumptions and develop new and more accurate models of the world. The redshift issue highlights a critical point about cosmology. We're dealing with immense distances and incredibly faint light. It's like trying to piece together a jigsaw puzzle where most of the pieces are missing, and the picture on the remaining pieces is blurry. We have to be humble about our knowledge and willing to admit when we're wrong. Furthermore, The implications of a flawed redshift understanding extend beyond just the distances to galaxies. It affects our estimates of the universe's age, its expansion rate, and the distribution of matter within it. If redshift isn't a reliable indicator of distance, then our entire cosmic picture could be skewed. The analysis continued. Scientists began looking at alternative methods for determining distances in the early universe, methods that didn't rely solely on redshift. They examined things like the sizes of galaxies, the brightness of supernova, and the distribution of elements within galaxies. Each method had its own set of assumptions and uncertainties, but by comparing the results from different methods, they hoped to get a more accurate picture of the distances to these early galaxies. Meanwhile, theorists were busy developing new models of the universe that could explain the James Webb Space Telescope observations without resorting to radical ideas like a varying speed of light. They explored models with different types of dark matter, different properties of dark energy, and different geometries of spacetime. They even considered the possibility that our universe is just one of many universes in a vast multiverse. The data reveals that the challenges presented by the James Webb Space Telescope are not just about individual observations, but about the entire framework of our cosmological understanding. What if the problem isn't just with redshift itself, but with our assumptions about how galaxies form and evolve? What if the early universe was simply a much more chaotic and dynamic place than we previously imagined? There's a significant challenge facing the community. It centers on how we interpret the pronouncements of Nobel laureates. It's easy to treat them as gospel, as if winning a Nobel Prize in one field automatically grants them expertise in all others. That's simply not the case. Every scientist, regardless of their accolades, is still bound by the limits of their own specialization. Consider this. A Nobel Prize in physics, for example, doesn't instantly make someone an expert in cosmology or astrophysics. While there's overlap, each field has its own nuances, its own established methodologies, and its own body of evidence. A brilliant physicist might offer a fresh perspective, but their insights need to be rigorously vetted by experts within the specific field they're commenting on. It's about respecting the depth of knowledge required to truly understand these complex topics. I think it's crucial to examine the specific statements made by any Nobel laureate with a critical eye, especially when they venture outside their core area of expertise. What evidence are they presenting? What assumptions are they making? Are their claims supported by the broader scientific consensus within the relevant field? It is very important to weigh what they're saying rather than blindly accepting it because of their reputation. We can't dismiss revolutionary ideas out of hand simply because they challenge the established order. Science progresses through the constant questioning of existing paradigms, but it's equally important to maintain a healthy level of skepticism towards claims that lack solid evidence or contradict well-established findings. The key is to strike a balance between open-mindedness and critical thinking. It is crucial to remember the history of science is littered with examples of brilliant minds who were ultimately proven wrong. Even Nobel laureates are fallible human beings, subject to biases and limitations in their understanding. Deferring to authority without questioning is a recipe for stagnation. Scientists discovered that the initial excitement surrounding some of these alternative theories began to wane as more data came in. While the James Webb Space Telescope did reveal some unexpected features in the early universe, many of these observations could be explained within the framework of the existing cosmological model, albeit with some modifications and refinements. For instance, some of the unexpectedly bright galaxies could be explained by higher rates of star formation than previously assumed. Others could be due to the presence of active galactic nuclei, supermassive black holes at the centers of galaxies that are actively accreting matter and emitting large amounts of energy. Theorists also refined their models of galaxy formation to better account for the observed properties of early galaxies. They incorporated more sophisticated treatments of gas dynamics, star formation, and feedback from supernovae and active galactic nuclei. These improved models were able to reproduce many of the features seen in the James Webb Space Telescope images without requiring any radical changes to our understanding of the universe. This isn't to say that the challenges posed by the James Webb Space Telescope have been completely resolved. There are still some lingering questions and puzzles that scientists are actively working to address. But the initial sense of crisis has largely subsided, replaced by a more nuanced and cautious approach. Scientists are now focusing on gathering more data, refining their models and exploring new theoretical ideas to explain the remaining discrepancies. They're also working to improve our understanding of the systematic uncertainties in the James Webb Space Telescope observations, to ensure that the conclusions they're drawing are robust and reliable. The James Webb Space Telescope has provided us with an unprecedented glimpse into the early universe, revealing a wealth of new information that is challenging our understanding of cosmology. But it's important to remember that science is a process of continuous refinement, where new observations are constantly being used to test and improve our theories. It's a journey of discovery, not a destination. This means that any pronouncements about the telescope breaking cosmology should be viewed with a healthy dose of skepticism. While the telescope has certainly revealed some unexpected features, it hasn't overturned our fundamental understanding of the universe. Instead, it has provided us with new insights that are helping us to refine and improve our models. Here's what's wild. There's a tendency to latch onto sensational claims, especially those that challenge established scientific consensus. It's human nature to be drawn to the extraordinary, the unexpected, the revolutionary. But it's important to remember that science is a slow, methodical process built on careful observation, rigorous analysis, and peer review. Science isn't about making grand pronouncements or seeking to overturn existing theories for the sake of it. It's about building a comprehensive and accurate understanding of the world around us, one small step at a time. The implications extend beyond just the James Webb Space Telescope. It speaks to the broader issue of scientific communication in the age of social media. In a world where information spreads rapidly and misinformation can easily go viral, it's more important than ever to be critical consumers of science news. We need to be able to distinguish between legitimate scientific findings and sensationalized claims, between expert opinion and uninformed speculation. We need to be able to evaluate the evidence for ourselves and make informed decisions about what to believe. The James Webb data just underscores the need for skepticism and critical thinking. What if we're putting too much faith in our current models and simulations? What if the universe is far more complex and unpredictable than we currently imagine? It's a question that drives scientific progress. Webb just revealed something massive. Our understanding of gravity might be incomplete. We've operated for decades under the assumption that dark matter explains the rotational curves of galaxies. But what if there's another explanation, one that challenges the very foundations of Newtonian physics? Enter modified Newtonian dynamics, or MOND. It's an alternative theory of gravity proposed by physicist Mordechai Milgram in the early 1980s. MOND suggests that at extremely low accelerations, gravity deviates from what Newtonian physics predicts. Instead of invoking dark matter to explain why galaxies rotate faster than they should based on their visible matter, MOND proposes that gravity itself behaves differently at galactic scales. Now, MOND has always been a bit of an outsider, a rebel theory challenging the established order. It hasn't been widely accepted by the scientific community, largely because it struggles to explain certain cosmological observations, especially those related to the cosmic microwave background and the large-scale structure of the universe. Dark matter, despite its own mysteries, fits more neatly into our current cosmological model, lambda CDM. But MOND does have one major strength. It accurately predicts the rotational curves of galaxies. In fact, it does so with remarkable precision, often outperforming dark matter models in this specific area. And that's where the James Webb Space Telescope comes in. If some of the early JWST observations continue to defy explanation within the standard dark matter framework, MOND might experience a resurgence. The telescope's ability to observe distant galaxies with unprecedented detail could provide new data that either supports or refutes MOND's predictions. It's not about replacing dark matter entirely, but it's about considering if MOND provides a more accurate description of gravity within galaxies themselves. The implications extend beyond just galaxy rotation. MOND also makes predictions about the internal dynamics of dwarf galaxies and the behavior of tidal dwarf galaxies, galaxies formed from the debris of larger galaxies interacting. Webb's observations of these systems could provide crucial tests of MOND's validity. Consider this: dark matter halos are thought to be spherical. MOND, on the other hand, doesn't require these halos, instead linking the observed gravitational effects directly to the distribution of visible matter. This difference in prediction could be tested by Webb through detailed observations of gravitational lensing, the bending of light around massive objects. Scientists discovered that if the light from a distant galaxy is bent by a foreground galaxy, the pattern of distortion can reveal the distribution of mass in the foreground galaxy. If dark matter halos are indeed spherical, the lensing pattern should reflect that. But if MOND is correct, the lensing pattern should be more closely aligned with the distribution of visible matter. The analysis continued with the examination of ultra-diffuse galaxies. These are galaxies that are very faint and have a low surface brightness. They are also thought to be heavily dominated by dark matter. Webb's ability to observe these galaxies in greater detail could help us to understand the distribution of dark matter within them and to test whether MOND can also explain their properties. Further examination revealed that MOND isn't perfect. It has its own set of problems. It struggles to explain the observed properties of galaxy clusters, which are much larger structures than individual galaxies. It also doesn't fit neatly into our understanding of the early universe. The evidence shows that MOND is not a complete theory of gravity, but it does raise some important questions about our understanding of the universe. It's entirely possible that the truth lies somewhere in between. Perhaps dark matter exists, but its effects are modified by a change in the laws of gravity at very low accelerations, as MOND suggests. This means that we need to keep an open mind and be willing to consider alternative explanations for the observations that we are seeing. The James Webb Space Telescope is providing us with a wealth of new data, and it is up to us to use this data to test our theories and to refine our understanding of the universe. It might mean accepting that our current models aren't the final word. And then there's the question of whether MOND is actually a manifestation of something even deeper that we don't yet understand. Is it a sign that our understanding of space and time is incomplete? Could it point towards new physics beyond Einstein's theory of general relativity? The implications extend to our fundamental understanding of the cosmos. If gravity behaves differently at different scales, it could have profound implications for our understanding of the formation and evolution of the universe. It could also affect our understanding of dark energy, the mysterious force that is causing the expansion of the universe to accelerate. Meanwhile, it's crucial to remember that science is a process. It's about constantly testing and refining our ideas based on new evidence. The James Webb Space Telescope is providing us with that new evidence, and it's up to us to follow where it leads, even if it challenges our most cherished beliefs. And if that leads to a revised understanding of gravity or a more nuanced picture of dark matter, then that's a scientific revolution worth embracing. It's a testament to the power of human curiosity and our relentless pursuit of knowledge. This means we might need to rethink how quickly galaxies could form in the early universe. The James Webb Space Telescope is peering back to a time when the universe was just a few 100 million years old. That's practically infancy on a cosmic scale. And what it's seeing is surprising. We're finding galaxies that are incredibly bright and massive, far more developed than our existing models predicted for that early epoch. One of the biggest surprises has been the sheer intensity of star formation within these early galaxies. We're talking about starbursts, periods of extremely rapid star formation that are far more vigorous than anything we typically see in galaxies today, or even in the comparatively recent universe a few billion years later. The problem is, these intense starbursts don't easily fit with our current understanding of how galaxies are supposed to form. In the standard model, galaxy formation is a gradual process. Small clumps of matter slowly merge together over billions of years, gradually building up larger and larger structures. Star formation is expected to be relatively slow and steady in the early stages, with occasional bursts triggered by mergers or other events. But the James Webb data reveals something different. It's showing us galaxies in the early universe that are essentially all in on star formation. They're churning out stars at an insane rate, far exceeding what our models predict is possible given the available time and resources. So, what's going on? One possibility is that we're underestimating the amount of gas that was available in the early universe. Gas is the raw material for star formation, so if there was more gas around, galaxies could potentially form stars more rapidly. However, this explanation has its limits. To explain the observed starburst intensities, we would need significantly more gas than our current models predict. Another possibility is that the conditions in the early universe were simply more conducive to star formation. Perhaps the gas was denser, or the temperatures were different, or the magnetic fields were stronger. Any of these factors could potentially boost the rate of star formation. But again, we need to understand why these conditions would have been so different in the early universe compared to later times. There's also the possibility that our understanding of star formation itself is incomplete. We have a pretty good handle on the basic physics of star formation, but there are still many details that we don't fully understand. Perhaps there are processes that we're missing that can significantly accelerate the rate of star formation under certain conditions. Consider the possibility that the very nature of the first stars was different. Population 3 stars, as they're called, were made up of almost entirely hydrogen and helium, the elements forged in the Big Bang. This lack of heavier elements could have led to them being much more massive and energetic than the stars that form today. If these behemoth stars were more common in the early universe, their intense radiation and powerful supernova explosions could have triggered even more star formation in surrounding gas clouds, leading to the observed starbursts. It's an idea, but a challenging one to prove. And then there's the elephant in the room: dark matter. Could dark matter be playing a more active role in galaxy formation than we previously thought? Perhaps dark matter halos, the invisible scaffolding around which galaxies form, were denser or more clumpy in the early universe. This could have led to a more rapid accumulation of gas and a higher rate of star formation. The problem is, many of these explanations require tweaking our existing models of galaxy formation. They require us to introduce new parameters or modify existing assumptions. And while that's not necessarily a bad thing, science is all about refining our models in light of new evidence, it does raise the question of whether we're missing something fundamental. It's important to remember that the James Webb Space Telescope is still in its early stages of exploration. We're only just beginning to scratch the surface of what it can reveal about the early universe. As we collect more data and refine our analysis techniques, we'll undoubtedly gain a better understanding of these intense starbursts and their implications for galaxy formation. But for now, they remain a puzzle. A fascinating puzzle to be sure, but a puzzle nonetheless. They challenge our current understanding of the universe and force us to confront the possibility that our models are incomplete. And that's exactly what makes science so exciting. It's about constantly pushing the boundaries of our knowledge and exploring the unknown. These early galaxies are so bright, so massive, so quickly formed, it's almost as if they shouldn't exist at all, according to our current theories. And that brings us to another potential issue: the size and mass of these early galaxies. You've been lied to about galaxy formation. For decades, the prevailing theory has been that galaxies form from the bottom up, small clumps of stars and gas merging over billions of years to create larger structures like our own Milky Way. It's a neat, tidy picture, and it's been the cornerstone of our understanding. But the James Webb data, it's throwing a wrench into the whole machine. These early galaxies, the ones shining brightly just a few 100 million years after the Big Bang, they're too big. They're too massive. And perhaps most perplexing, they seem to be too mature. They have well-defined spiral arms and central bulges, features we thought took eons to develop. So, how did they get there so quickly? The sheer size of these galaxies is a problem. Our current models struggle to explain how so much matter could have accumulated in such a short amount of time. Gravity, as far as we understand it, simply couldn't have pulled everything together that fast. It's like watching a tree grow to full size in a single day. It defies common sense. And then there's the issue of heavy elements. These early galaxies are surprisingly rich in elements heavier than hydrogen and helium, elements that are forged in the hearts of stars, and then scattered throughout the universe in supernova explosions. The presence of these heavy elements suggests that these galaxies have already gone through multiple cycles of star formation and death, something that, again, shouldn't be possible in such a young universe. This has led some astronomers to propose a radical new idea. What if galaxies actually form from the top down? What if, instead of merging from smaller clumps, they condense directly from massive clouds of gas and dark matter? This top-down model suggests that the early universe was filled with vast, turbulent clouds of primordial gas. These clouds, seeded with fluctuations in density, could have collapsed under their own gravity, forming the cores of galaxies in a matter of just a few 100 million years. Now, this isn't a completely new idea. Top-down models have been around for a while, but they've largely been dismissed because they struggled to explain certain features of galaxies, like the distribution of stars and the presence of supermassive black holes at their centers. But the James Webb data is breathing new life into these models, forcing us to reconsider whether they might be more accurate than we previously thought. Consider this. If galaxies formed from the top down, it could explain their rapid formation and their early enrichment with heavy elements. The collapse of a massive gas cloud would trigger a burst of star formation, quickly creating a population of massive stars that would then explode as supernova, seeding the galaxy with heavy elements. It could also explain the presence of supermassive black holes, which could have formed directly from the collapse of the central region of the gas cloud. Of course, the top-down model also has its challenges. It's not clear, for example, how it can explain the diversity of galaxy shapes and sizes that we see in the universe today. If all galaxies form from the collapse of massive gas clouds, why aren't they all roughly the same size and shape? And then there's the question of angular momentum. As a gas cloud collapses, it tends to spin faster and faster, like a figure skater pulling in their arms. This rapid rotation can prevent the cloud from collapsing completely, leading to the formation of a disc-shaped structure rather than a spherical galaxy. How did these early galaxies overcome this problem of angular momentum? One possibility is that the early universe was more turbulent than we thought, with frequent collisions and mergers between gas clouds. These collisions could have disrupted the rotation of the clouds, allowing them to collapse more easily. Another possibility is that dark matter played a more important role in the early stages of galaxy formation, providing the gravitational scaffolding needed to overcome the effects of angular momentum. It's also worth noting that the top-down and bottom-up models aren't necessarily mutually exclusive. It's possible that galaxies form through a combination of both processes, with some galaxies forming primarily from the top down and others forming primarily from the bottom up. The relative importance of these two processes could depend on the initial conditions in a particular region of the universe. The analysis continued. Researchers began to focus on the internal dynamics of these early galaxies, looking for clues about their formation history. They examined the distribution of stars and gas, the rotation curves of the galaxies, and the chemical composition of their stellar populations. The data revealed some surprising results. Some of these early galaxies appeared to be rotating much faster than expected, suggesting that they were denser and more compact than our current models predict. Others showed signs of recent mergers, indicating that they were still in the process of forming. These findings suggest that galaxy formation in the early universe was a much more complex and dynamic process than we previously thought. It's not simply a matter of small clumps merging to form larger structures. It's a messy, chaotic process involving the interplay of gravity, gas dynamics, and dark matter. And the James Webb Space Telescope is giving us a front-row seat to the show. The implications extend beyond just our understanding of galaxy formation. If our models of galaxy formation are wrong, it could also have implications for our understanding of the evolution of the universe as a whole. Galaxies are the building blocks of the cosmos, and their formation and evolution are intimately linked to the evolution of the universe itself. If we don't understand how galaxies form, we can't fully understand how the universe evolved to its present state. This means, it means a lot of work is ahead, a lot of rethinking, a lot of simulations to run. The old models? They're likely headed for the trash heap. And then there's another factor to consider, the role of active galactic nuclei, or AGN. Our current understanding of the universe is likely incomplete. The James Webb Space Telescope isn't just refining our models, it's potentially demanding a complete overhaul, and part of that overhaul has to include a more nuanced understanding of active galactic nuclei. A GN, powered by supermassive black holes at the centers of galaxies, are like cosmic engines. They can spew out enormous amounts of energy, radiation, and particles. This output can dramatically influence the evolution of their host galaxies. Consider this. If an AGN is actively feeding, it can unleash powerful jets of plasma that extend far beyond the galactic disk. These jets can heat up the surrounding gas, preventing it from cooling and collapsing to form new stars. It's like a galactic thermostat, regulating star formation. But it gets even more complicated. The radiation from an AGN can also ionize the gas in the host galaxy, stripping electrons from atoms. This ionization can also suppress star formation. Furthermore, the intense gravitational forces near the black hole can disrupt the orbits of stars and gas clouds, further hindering the formation of new stars. So, are AGN primarily destructive forces, preventing galaxies from reaching their full potential? or do they play a more constructive role? Some research indicates that AGN can also trigger star formation under certain circumstances. For example, the outflowing gas from an AGN can compress surrounding gas clouds, causing them to collapse and form new stars. It's a complex balancing act. The interplay between AGN feedback and galaxy evolution is one of the biggest puzzles in modern astrophysics, and JWST is uniquely positioned to provide new insights into this process. Its ability to observe infrared light allows it to peer through the dust and gas that obscure the central regions of galaxies, revealing the inner workings of AGN and their host galaxies. Scientists have already begun using JWST to study the AGN in some of the earliest galaxies in the universe. The initial results are fascinating. They suggest that AGN were much more common in the early universe than we previously thought. This implies that they may have played a more significant role in shaping the evolution of early galaxies. Here's what's wild. Some of these early AGN appear to be much smaller than the AGN we see in the local universe. This suggests that black holes may have grown much more rapidly in the early universe than we previously thought. How did these black holes get so big so fast? That's one of the biggest unanswered questions in astrophysics today. JWST is also being used to study the impact of AGN on the surrounding intergalactic medium. The intergalactic medium is the tenuous gas that fills the space between galaxies. It contains most of the baryonic matter in the universe, the normal matter made up of protons and neutrons. A GN can have a profound impact on the intergalactic medium. The radiation from an AGN can heat up the intergalactic medium, preventing it from cooling and collapsing to form new galaxies. A GN can also enrich the intergalactic medium with heavy elements, the elements heavier than hydrogen and helium. These heavy elements are produced in the interiors of stars and then ejected into the intergalactic medium through supernova explosions and AGN outflows. The distribution of heavy elements in the intergalactic medium provides valuable clues about the history of star formation and galaxy evolution in the universe. JWST is being used to map the distribution of heavy elements in the intergalactic medium, providing new insights into the impact of AGN on the evolution of the universe as a whole. The analysis continued. Webb's future missions are already being planned, with the telescope expected to operate for at least another decade, possibly even longer. What are some of the key areas where JWST will continue to push the boundaries of our knowledge? Firstly, expect even deeper dives into the early universe. Astronomers will use JWST to search for the very first galaxies that formed after the Big Bang. These galaxies are incredibly faint and distant, making them difficult to observe with even the most powerful telescopes. But JWST's unprecedented sensitivity and resolution make it uniquely suited for this task. Secondly, JWST will continue to probe the mysteries of exoplanets. It will be used to study the atmospheres of exoplanets, searching for signs of water, methane, and other molecules that could indicate the presence of life. It will also be used to image exoplanets directly, providing us with our first glimpses of these distant worlds. Thirdly, JWST will be used to study the formation of stars and planets in our own galaxy. It will be used to observe the clouds of gas and dust where stars are born, providing new insights into the processes that lead to star formation. It will also be used to study the disks of gas and dust that surround young stars where planets are thought to form. And then there's the unexpected. The discoveries that we can't even imagine right now, the things that will truly rewrite the textbooks. That's the beauty of exploration. You set out to answer certain questions, but you often end up finding something completely different, something far more profound. 600 galaxies, all breaking the rules. That's the situation we're facing after the initial flood of JWST data, and it's leading some to ask a very uncomfortable question. What if our entire understanding of cosmology needs a major overhaul? The issue isn't just a few outliers, it's a systemic problem. These early galaxies are far too massive, far too bright, and far too evolved for their supposed age. According to our current models, galaxies simply shouldn't exist in such a mature state so soon after the Big Bang. They should be smaller, more chaotic, and less structured. But the JWST is showing us something else entirely, something unexpected. Consider the implications. If these galaxies are indeed as old and massive as they appear, It throws a wrench into our understanding of how dark matter coalesced, how quickly stars formed, and how supermassive black holes grew in the early universe. The existing simulations, painstakingly built over decades, simply can't account for what we're seeing. They predict a gradual, hierarchical buildup of galaxies, with smaller structures merging to form larger ones over vast stretches of time. The JWST data paints a different picture, one of rapid, almost explosive galaxy formation in the early universe. It suggests that the processes at play were far more efficient and accelerated than we previously thought. This could mean that our understanding of fundamental physics, such as the nature of dark matter and dark energy, is incomplete or even incorrect. Some scientists are suggesting that we need to revisit the very foundations of our cosmological models. Perhaps the standard model of cosmology, known as lambda CDM, needs to be modified or even replaced. This model, which has been remarkably successful in explaining many aspects of the universe, relies on the existence of dark matter and dark energy to account for the observed expansion rate and structure formation. However, the JWST data raises the possibility that dark matter may behave differently than we currently assume, or that its abundance in the early universe was significantly higher. Alternatively, dark energy, the mysterious force driving the accelerated expansion of the universe, may have played a more significant role in the early stages of galaxy formation. Of course, it's important to emphasize that these are just preliminary interpretations. The JWST data is still being analyzed, and it will take time to fully understand its implications. But the initial findings are certainly intriguing, and they suggest that we may be on the verge of a major paradigm shift in our understanding of the cosmos. Think about the sheer scale of what we're talking about here. We've built an entire framework of knowledge, a cosmic story that explains where we came from and how the universe evolved. And now this new data is forcing us to confront the possibility that parts of that story are wrong. It's a humbling experience, but it's also incredibly exciting, because it means we have the opportunity to learn something truly new and profound about the universe. The challenge now is to develop new theoretical models that can explain the JWST observations. This will require a collaborative effort from astronomers, physicists, and cosmologists around the world. They will need to incorporate new physics, refine existing simulations, and explore alternative scenarios for galaxy formation. It will be a long and arduous process, but the potential rewards are immense. Imagine a future where we have a more complete and accurate understanding of the universe, where we can trace the evolution of galaxies from their earliest beginnings to their present-day forms, where we can unravel the mysteries of dark matter and dark energy. The JWST is giving us a glimpse of that future, and it's a future worth striving for. What if, for instance, the universe went through a period of accelerated expansion much earlier than we thought? This early dark energy could have seeded the rapid growth of galaxies we're now observing. Or perhaps our understanding of gravity itself needs tweaking on cosmological scales. Modified Newtonian dynamics, MOND, for example, proposes alterations to gravity that could explain certain galactic behaviors without invoking dark matter. These are fringe ideas, sure, but ideas that are getting a fresh look in light of Webb's findings. Scientists discovered something else. The James Webb isn't just showing us these mature galaxies. It's showing us a surprising abundance of supermassive black holes in their centers. These black holes are far too large for their host galaxies, according to our current understanding of black hole growth. How did they get so big so quickly? Were they seeded by primordial black holes formed in the very early universe? Or did they grow through some other, more efficient mechanism? These are just some of the questions that the JWST is raising. And while they may seem daunting, they represent a tremendous opportunity for scientific progress. The telescope is not just confirming our existing theories, it's challenging them, pushing us to think outside the box and forcing us to confront the limits of our knowledge. The analysis continued. The journey of scientific discovery is rarely a smooth and linear one. It's filled with unexpected twists and turns, with moments of frustration and moments of exhilaration. But it's always driven by a relentless curiosity, a desire to understand the world around us, and a willingness to challenge conventional wisdom. The James Webb Space Telescope is a testament to that spirit. It's a tool that's helping us to push the boundaries of human knowledge, to explore the universe in new and unprecedented ways, and to uncover the secrets of our cosmic origins. The implications extend far beyond the realm of astrophysics. They touch upon fundamental questions about the nature of reality, the laws of physics, and our place in the universe. Are we alone in the cosmos? Is there life beyond Earth? What is the ultimate fate of the universe? These are questions that have captivated humanity for centuries, and the JWST is helping us to get closer to answering them. Here's what's wild. The JWST's discoveries are not just relevant to scientists and researchers. They're relevant to everyone, because they remind us that we are part of something much larger than ourselves, that we are connected to the cosmos in ways that we are only beginning to understand, and that the quest for knowledge is a never-ending journey, a journey that we all share. And then there's the human element, the sheer ingenuity and dedication required to build and operate a telescope as complex as the JWST is truly awe-inspiring. It's a testament to the power of human collaboration, to our ability to overcome seemingly insurmountable challenges, and to our unwavering pursuit of knowledge. It's a symbol of what we can achieve when we work together to explore the universe and unlock its secrets. The James Webb Space Telescope isn't just a scientific instrument. It's a symbol of hope, a symbol of progress, and a symbol of our shared human destiny. And its journey has just begun. So, what does it all mean? The James Webb Space Telescope is showing us a universe that is far more complex and mysterious than we ever imagined. It's challenging our existing theories, raising new questions, and opening up new avenues of research. And while it may be unsettling to realize that our understanding of the cosmos is incomplete, it's also incredibly exciting, because it means that we have the opportunity to learn something truly profound about the universe and our place in it. If you enjoyed this exploration of the JWST's discoveries, be sure to subscribe for more deep dives into the latest science and space news.